Yeah, thanks so much for the invitation. It's really nice to be speaking here. This is a really nice seminar, I think. Okay, so having some. All right, so I'm going to talk about a couple of things about using quantitative hyperelliptic regularity, especially to understand dynamical properties of SDEs. And the kind of SDEs that I'm interested in are actually motivated by turbulence. So turbulence is something that can only happen in infinite dimensions. So let's just clear that up right there. So it's something that you observe in infinite dimensional weakly dissipative systems of a general type. So usually this is volume preserving in phase space formally, and it satisfies at least one energy conservation law. And then you have a usually linear damping with a small parameter, and then you impose a driving force, and you first send time to infinity, let it settle into a statistical steady state, and then you send epsilon to 0. So this is just one regime of turbulence. This is called statistically steady turbulence. It's the most commonly studied. It's in some sense the simplest type of turbulence. And there's a lot of properties that are universal to turbulent systems. Each one is different, but there's a lot of properties that are universal. I'm just going to highlight. Actually, I'm just going to highlight these two because these are the only two that really have an analog in finite dimensions, which is ergodicity. Simply says that you have a unique long-term, or in this case, I'm going to mean that it has a unique long-term ensemble statistics. So all time averages of any experiment converge to a unique ensemble statistics. Then you also get chaos. So you have an extreme sensitivity to initial conditions, which means that if you change initial conditions a little bit, you get very different solutions. And I'll explain what this means later. Of course, one of the other hallmarks of turbulence that does not have an analog in finite dimensions is anomalous dissipation, which essentially says that it sends. So suppose you're injecting energy at order 1 scales, then what happens is that the nonlinearity sends this energy from, for example, large scales down to small scales, where it's dissipated by the dissipative term at a constant rate that doesn't depend on epsilon. So this, of course, cannot happen in finite dimensions. So if you're studying statistically steady turbulence, if you have a random system, then many of these examples, you can prove that there exists a unique stationary measure, which I'll define rigorously on the next slide. But it basically tells you have statistics which stay constant as a function of time. So solutions are obviously varying quite a lot, but the statistics aren't changing. Once you have this object, you can formulate almost any question you can imagine about turbulence in a mathematically precise way. The two ones that I'm going to be talking about, because they have analogs in finite dimensions, are understanding how does this ergodicity property break down, or how does it behave as you send epsilon to 0? So is it true that, for example, the statistics of each individual experiment converge to the ensemble statistics at a rate which maybe doesn't diverge too badly in epsilon or something like that? The second thing, of course, is to prove that when epsilon is small, when the dissipation is weak, that you have chaos indeed. And then, of course, you can formulate tons and tons of other problems, tons of other questions about the infinite dimensional nature of turbulence. So with the exception of a few toy models that don't satisfy all these properties, so don't satisfy chaos, for example, and more recently some work that Alex Blumenthal, Sam Punch, and Smith and I did in the last couple of years on a sort of relatively easy but still physical turbulence system called Bachelor regime passive scalar turbulence. Aside from these cases, basically nothing is known about statistically steady turbulence. And as it happened, even the finite dimensional analog, so what little of it exists in finite dimensions, these questions were also completely open. And so one of the things that we tried to do during lockdown was sort out some of the finite dimensional analogs of these questions as best we could, and sort of close up that angle of this question. So that's the motivation for the type of SDEs we're going to study. So this means I'm going to study the following SDE where dimension should be big. And I have a linear damping, symmetric positive definite damping. Does not have to be diagonal because you want it to be something like viscosity or hyperviscosity or something like that. And we have a nonlinear bilinear term. That's like the analog of the Euler nonlinearity in fluid mechanics. So it satisfies two main properties that we're going to assume. It's divergence free, so it's volume preserving in phase space, and it conserves energy. So this x squared would be a conserved quantity for the nonlinear deterministic system. And then I want to understand the epsilon to 0 dynamics when I force with additive forcing. So right now I'm just going to talk about stochastic forcing, where this is a constant. And I'll call these Euler-like systems because Galerkin truncations of the incompressible Navier-Stokes fits into this framework. So if you study Navier-Stokes on a torus, break it into Fourier modes and write down the evolution of the Fourier modes and then truncate it, you get a system like this. And there's other systems of this form as well. Now, the first thing you notice is that because you have no anomalous dissipation of energy, the energy of this system, you try to send epsilon to 0, you have an epsilon damping, and you have an order 1 forcing. So the energy is going to diverge like 1 over epsilon as you set epsilon to 0. So that does not have a reasonable limit as epsilon goes to 0. So instead, I'm going to redefine x and t and actually epsilon, but I'm just going to use the same notation. I'm not going to introduce epsilon twiddles or something. Basically, what you want to do is you want to rescale space and time, or rescale the amplitude of x and time, to make it a small noise limit problem. So now the energy will remain order 1 as epsilon goes to 0. And you see it becomes a small noise problem because here the energy was going to infinity, and if the energy goes to infinity, then this term dominates. And so the problem becomes more and more deterministic as you set epsilon to 0. So that's why you should be expecting a small noise limit problem if you want to study this. So this is going to be the kind of SDE problem that we study. Now these SDEs, it's not too hard to prove that you have a very nice, almost sure global well-posedness theory. So almost every solution is globally well-posed, doesn't diverge to infinity, and you get uniqueness and stability. So you can define Markov kernels, which essentially says what is the probability. It's a measure which tells you if you know the initial condition, what is the probability that your dynamics ends up in some set A. And from that, you can derive Markov semigroups, one on observables. So this tells you if you know the initial condition, then what is the expected value of a certain statistical question that you might ask. That's PT phi. And then its dual is PT star, which tells you if you know the initial law of the solution, then PT star tells you how the law evolves as a function of time. So a really important quantity are stationary measures. So these are measures for which PT star, it's a fixed point of PT star. So this tells you if you randomize the initial condition with respect to this measure, these statistics don't change. The individual solutions are moving all over the place, but the statistics are the same. So what you should have in mind, actually, if you look at water over a stone in a river, and just look at it for a few minutes and think about it, you're looking at a statistical stationary solution of basically 3D Navier-Stokes. So that's what a statistical stationary solution will essentially look like. How to prove existence and uniqueness is very well understood. So if you're not familiar with it, that's okay. I'm just going to be working in cases where this is all known how to do. So I'm going to be working under the assumption where you have a unique stationary measure. It's not too difficult to prove this sort of thing nowadays. So this tells you that for these random systems, you do have a unique long-term statistics of all the initial conditions. Okay, so let's think about these Markov semigroups a little bit. So in finite dimensions, so if you took an SDE course, then you would know that these Markov semigroups solve PDEs, of course, deterministic PDEs. And they're adjoints of each other. So you have L and L star. Here I'm using vector field notation. So given a vector field, I can associate the differential operator in that direction. It's like a directional derivative notation. So you have a first order drift term, and then you have second order terms coming from the forcing. And if you force every mode in your problem, so if you force all the directions, then these operators would be elliptic. They would just be elliptic operators, and then they would be instantly regularizing and all that fun stuff. We don't want to do that generally. So Hörmander in 1967, he codified an essentially sharp condition for how do you prove regularization, for example, of these Markov semigroups, even if you only force a couple of the directions. So if these guys don't span the tangent space. It's a little bit complicated. Basically, what you want to do, roughly speaking, you want to look at commutators. And essentially, let's ignore this small detail about let's ignore the details. Just think, if I take enough commutators, do I eventually span the tangent space? So this is what the Hörmander spanning condition means. It's not just saying that you have to that the original vector span, but enough commutators of the original vector can span. That's sufficient and almost necessary. And notice that this involves the nonlinearity quite importantly. It's essentially a condition coupling the nonlinearity and the forcing directions. Okay, so now the first thing I want to study is sort of question 1 on that list of turbulence questions. So in finite dimensions, can I quantify how quickly I converge to the stationary measure? And can I get uniform estimates on the stationary measure? So can I get at least some information on mu epsilon as epsilon goes down to 0? So this is a project that my graduate student Kyle Lees and I did this year. So the first thing is, what can we say about the stationary measure? So let rho epsilon be the density. Whoops. Right. So let rho epsilon be the density of mu. So mu, if you have hypoellipticity, so we're assuming that you have a Hörmander spanning condition, then mu epsilon is actually smooth. So the interesting question isn't regularity for positive epsilon. The more interesting question is, what do you get when epsilon goes down to 0? How much regularity do you get? So what we can prove is a uniform Gaussian upper bound on these measures and uniform boundedness on compact sets. And so that's interesting, because even if you're only forcing 4 or 5 out of a million modes in your system, the solution will still spend, on any given ball, it'll still spend about a uniform amount of time everywhere in epsilon as epsilon goes down to 0. So that's what the lower bound of the stationary measure will mean. And then these uniform estimates, you'll be able to pass the limit and construct a stationary measure for the deterministic problem, which has a little bit of regularity. So here S is fractional, between 0 and 1, and is L infinity. In fact, it has this Gaussian upper bound. Once you have that, you can actually use that. So that was actually in some sense a lemma, though it's, in my opinion, intrinsically interesting. It was a lemma in trying to quantify this convergence to equilibrium of the laws. So what we can prove is the following Sharp theorem. So don't worry too much about the norms. It's a weighted total variation space. So if you take any law that's sufficiently well localized, if you evolve it, it converges to the unique stationary measure exponentially fast, and you can quantify the rate. So in particular, delta and k don't depend on epsilon. So it's just minus epsilon delta t. And this is sharp. So this is sharp up to the precise numerical values of k and delta. And that's actually much easier to see than this estimate. So this estimate cannot really be improved. Okay, so how do you go about proving something like this? Of course, you want to sit down, you want to collect what information do I have about the stationary measure? Let's look at that first. So the stationary measure is a solution to this PDE. So, and of course, I'm working in the additive noise case. So X star is basically, this is for the forcing directions. So forcing directions are constant vector fields. The first thing is the energy estimate tells you that the drift condition, it doesn't make solutions bigger or smaller. It just rotates solutions around the spheres. And so if you're looking at how big a solution is, how far away it can get to infinity, it's just a function of the noise and the sort of damping. And you can prove that this implies a Gaussian estimate, which is uniform in epsilon. This is because the forcing and the damping have been rescaled so that they're balanced. So that's good. You have a Gaussian L1 estimate. Next thing, of course, the first thing any PDE person would do is multiply the equation by rho and integrate by parts. And if you do that, the other property of the nonlinearity, the fact that it's volume preserving in phase space, means that big term also vanishes from that estimate. And you just get that the L2 norm of the forcing direction derivatives are bounded by the L2 norm of the solution. However, the L2 norm of the solution is not something that you know a priori. So that's important to point out. Now, Hörmander observed that you have one other really important a priori estimate, which is less obvious, which is now if we multiply by a test function, just any old test function, we actually see that this estimate plus the Kolmogorov equation implies one more estimate, which is sort of an H-1 regularity estimate in the forcing directions. So you have H-1 in the forcing directions. on the drift field. So the drift vector field, you have some regularity in the drift vector field in h minus 1 uniformly in epsilon. Again, it's uniform in epsilon. Actually, it's better than uniformly in epsilon. You actually have an epsilon here. And that's kind of a hint about the fact that your solutions actually, rho is actually going to converge to a deterministic stationary measure. Okay, so how do we use that information to deduce uniform in epsilon estimates? So this is the simplest of the uniform Hörmander inequalities that I'm going to talk about today. And this is basically in Hörmander's paper with some slight variation. So if you have a vector field, now my vector fields are indexed by epsilon. So you need to say that there's somehow, they need to be, the particular vector fields I'm discussing, it's kind of clear that they're well behaved as epsilon goes down to 0. But in general, you need to impose some conditions. And essentially what it says is there exists some fractional regularity, which is controlled by the L2 norm plus these two natural norms that come up in the a priori estimates. So this was the positive h1 in forcing directions, or h1 dot in forcing directions. And this is the h dot minus 1 in forcing directions. Or is the h dot minus 1 of x0. And it says that these two actually combine to give you some positive regularity. And this lemma is pretty easy to prove. It's not easy to prove, but it's easy to prove if you have Hörmander's paper in front of you and are patient enough to read it carefully. And Hörmander proved basically this a priori estimate using a combination of two ideas. So first of all, you can show that if you have positive regularity in this direction, so if you have positive regularity in a set of vector fields whose commutators span, you can get positive regularity in all directions. This is not at all obvious, but this is the easier part of Hörmander's paper. It's all based on this formula, which tells you that if you sort of look at finite differences in directions that you have control on, you can actually extract finite differences in commutators of those directions. And those are new directions, actually. And so you get a little bit of intermediate regularity in all these other directions. And you can then fill out all directions and get regularity in all directions. Then the issue, the actually much more subtle issue, is how do you get positive regularity in the x0 direction? Because that's not obviously something you already have. That is a very subtle regularization procedure, and it's a little bit. It's impressive that Hörmander's approach actually closes. It's definitely too technical for me to explain, but it's the hard part of the paper in some sense. Once you have that, though, you can get an a priori L2 estimate because you know that this only diverges at a certain rate, and you can interpolate against the drift bound, which tells you that the solution at infinity is very small. And so you can interpolate this gain in integrability against the L1 control. And this is your next a priori estimate, or your next estimate independent of epsilon. From there, things get a little bit more complicated if you want to prove the estimates that we have. So there we sort of combine uniform Hörmander inequalities with some ideas from Kolmogorov, Moser on, so their paper was on kinetic Fokker-Planck. So some of those ideas are specific to kinetic Fokker-Planck, but some of those ideas can still be extracted and used in much more general settings than they're using them in. So the upper bound is actually not too hard. It's very similar to a Moser iteration as in the elliptic case, except instead of Sobolev embedding to gain integrability, you use this uniform Hörmander inequality instead. The lower bound is harder, so especially getting in an epsilon independent way. So here you're going to use a Giorgi, kind of like what you use when you use Holder regularity for elliptic equations with Giorgi's approach, but it's harder. So you need to control the oscillation of subsolutions in a uniform and epsilon way. But since you don't have a Sobolev estimate, it's harder to do. But you can use a kind of compactness rigidity argument that's sort of like what's in Kolmogorov, Moser, and Vasur's paper. And you also need some other new ideas. I think the key thing to controlling the oscillation in the end, aside from a variation, slightly more complicated variation of the uniform Hörmander estimate that I showed, is you need this rigidity lemma, which says that if you have a function which is constant in in a set of vector fields whose commutators span the tangent space, then that function actually has to be constant. And it's actually proved using a local controllability argument. This basically tells you that you can't violate the sort of control of oscillation lemmas. So that's roughly how you get a lower bound. Now, proving the geometric ergodicity is actually a little bit more involved. So let me just give you an idea. So first of all, there is one norm where you have control. So we're going to do it by duality. So we're going to estimate that PTF converges to the integral of f d mu for f an observable. So if you look at this norm, so there's one norm which is L2 weighted with mu epsilon. This is the norm in which you have a nice, so you have a nice actually monotone estimate. Well, it's actually not an estimate, it's an identity. So the problem is that you don't really have any idea how to prove a Poincaré inequality, which would tell you this. So that's too much to hope for. So that's not going to happen because you don't really know enough about mu epsilon, and it's probably false. So you need to use a different framework. So the framework we use is based on Harris's theorem, which I'm not going to go through the whole thing. But the main difficult step is the following quantitative irreducibility. So it says that if I take two initial conditions, so let's say this is the origin, I want to say that after time 1 over epsilon, the law of x and y has to overlap in a way that doesn't depend on epsilon. So eta is independent of epsilon here. This is sharp. This is the best estimate you could hope for, because if x and y start at different energy levels, no matter what the nonlinearity is doing, the law is going to be kind of concentrated near, in an annulus, kind of near the initial condition, and this is going to spread out something like order square root of epsilon t, because it can't cross energy levels really faster than if the nonlinearity wasn't there. So this is sharp. And similar reasoning shows you that the whole geometric ergodicity of time scale like 1 over epsilon is sharp. So you can't improve that estimate. So now we have to deduce this. And this is, not so easy. Basically, we use what's called a weak Poincaré framework. And this is about showing that, so a weak Poincaré inequality is where you're going to control. So remember, we had this kind of estimate. This was the time derivative of this quantity. So you can't control it back in terms of just PTF minus F, but you can control it in terms of PTF minus F plus some error terms. So you have to lose. You kind of have a lossy Poincaré. Maybe I'm not going to write out the whole thing, but yeah, you sort of have a lossy Poincaré. So what you're going to do is you're going to lose in L infinity, and you can use the fact that L infinity is actually propagated by PT, and produce a slow decay estimate of this type, and couple it with the uniform or really optimal quantitative kind of parabolic type regularization, L2 mu epsilon to L infinity regularization. And then if you fiddle around with it, then you can get the sharp theorem. So there's a lot of things I'm skipping, of course. But the key is to use a weak Poincaré framework. And it's very crucial that you have two things. In order to get the weak Poincaré inequalities and this regularization, you need more subtle uniform Hörmander inequalities that are now kind of a parabolic type. So space-time regularization. Kind of like, when you control L2, when you might want to control L2 HS in terms of L2 H.1 and L infinity L2, stuff like that. But now for hypoelliptic equations. So that's more complicated, and it definitely uses also the uniform upper and lower bounds on mu epsilon. So those are kind of critical for getting this estimate. Okay, so the next set of results that I wanted to talk about are results on kind of a more dynamical systems flavor, in particular proving chaos. So this is the other kind of hallmark of turbulence that has an analog in finite dimensions. So chaos is really recognizable as important to our understanding of what turbulence really is. And how I'm going to study chaos right now is with studying the top Lyapunov exponent. So this is studying the asymptotic exponential growth rate of the flow map, of the solution map. So phi is the solution map that takes the initial condition to where it evolves given the random forcing path. And what I want to prove is that this thing is almost surely positive, strictly positive. So as time goes infinity, you get exponential sensitivity to the initial condition, and at least in an infinitesimal sense. For deterministic systems, this is extremely hard to estimate, and very little estimates are known for wide classes of deterministic systems. For random systems, it's also very hard to estimate. There are actually a few tools at least, and we're going to introduce another new tool for estimating the Lyapunov exponent for SDEs, for SDE systems, for stochastic differential equations. So the simplest, I want to highlight this SDE because it's the first one that we were able to prove chaos for, that at least in terms of systems that it was unknown for, which is a famous model in applied mathematics called Lorenz 96. It was originally proposed for 40 unknowns, but it makes sense for any number of unknowns. So you have a periodic chain of unknowns, so that they're indexed by n, and it loops around in periodic loop. And then you have an epsilon damping, and you have stochastic, and I'm going to put stochastic forcing, so I'm talking about stochastically driven Lorenz 96. But it's very commonly used. It's very chaotic when epsilon is small, or so we think, when you actually look at the numerical simulations. So for example, this is time, and this is, each slice here is a value of these unknowns. So it's more than just chaotic. It's also has sort of completely crazy turbulent-like dynamics as you send a dimension larger and larger. So despite the numerical evidence that it's chaotic when epsilon is small, there was no mathematical proof of that, even in the stochastically driven regime. So that's one of the things that we're going to resolve. Okay, so the first thing is, how do you define a Lyapunov exponent mathematically? There's a beautiful theorem called the multiplicative ergodic theorem, which it says a lot of things, many more things than what I'm going to talk about in this talk. But one thing it tells you is it tells you that there is a top Lyapunov exponent for these SDE systems, and it's unique. And every trajectory almost surely reaches this Lyapunov exponent. So there's one, it's a deterministic number that just is a property of the system. And there's also so this gives you an asymptotic separation of trajectory estimate. It tells you kind of asymptotically how quickly do small changes in the initial data amplify. This estimate tells you, or it's not an estimate, this identity tells you, okay, apparently I misspelled asladet. I swear I checked that before, but I always mess it up. Thank you. So there's missing an E missing. Yeah, and then there's an asymptotic exponential volume compression or expansion rate. So you're studying the logarithm of the determinant of the Jacobian matrix. This is also a deterministic fixed quantity. So how does one actually estimate it? So this abstract theorem tells you that these quantities exist, but we want to understand how do we get any estimates on them. So I'm going to discuss it's a great idea. It goes back in the dynamical systems literature, maybe to the 60s. Let me explain it on just a general SDE, because it has nothing to do with our particular class of SDEs. So you take a general SDE in Stratanovich form. What we want to study is the normalized gradient of the stochastic flow. So this is going to live on a sphere. It solves an SDE on the sphere in Stratanovich form. Notice that it involves xt though, and this v is sort of a normalized gradient vector field. So VT is not a Markov process because of the presence of xt. So the process that you're actually interested in is the coupled process, the joint process xt-vt. So this is what we're going to call the projective process, because it evolves on the sphere bundle, or equivalently the projective bundle. because you don't really care about the difference between v and minus v. So what this tells you is you have a initial position and linear subspace, and it's going to evolve to another location and another orientation of vt, like that. And it solves a Stochanovich form SDE. So these twiddles will be the vector fields lifted onto the projective bundle or the sphere bundle. So why do we care? So this process actually knows about the stretching and compression in the flow map. So think about this very simple SDE. Sorry, not an SDE, this simple ODE. And if you think about what happens when you normalize the solution to this problem. So what happens is if you have a linear subspace, so VT is like a subspace here, what will happen is that this will tip down closer and closer to the x-axis as time goes forward. So even though it's not growing, VT is not growing in any sense, it still knows about the growth. It's compressing. It's compressing. It's concentrating on the x-axis. There's a beautiful identity called the Furstenberg Khasminski identity, which confirms that these Lyapunov exponents lambda sigma and lambda 1. So here n is the dimension of the phase space. I think I called it n before. So n equals d in this talk. That indeed the Lyapunov exponents are can be seen as an average volume compression, both in the original space, in the original phase space, and in the projective bundle space, in the sphere bundle space. And if you're dealing with additive noise, it's much easier to see, right? Then it's just the divergence of the vector field. It's much simpler. So the issue with this is that you don't really know what, I should emphasize, here it's phrased in terms of a stationary measure on the sphere bundle of the projective process. And that's a crucial thing. So we're going to be working where cases where we have a unique stationary measure of not only the x process, but also the xv process. And then you can do this. Right, so the problem is you don't know what those measures do. I mean, we spent a lot of time studying the measure mu, epsilon, as epsilon goes down to 0, but it's not like we really know everything. We just have kind of general upper and lower bounds. It's not enough to understand this integral directly. So we set about and we wanted to find a new way of estimating Lyapunov exponents. And we found the following identity, which is in terms of something called a Fisher information. So let me just focus on this one. So F is the density of the stationary measure for the projective process. And it says that if you look at the Fisher information just in the directions of the forcing, this actually identically balances this gap in Lyapunov exponents. And there are other expressions. So same thing on the row process, you get Fisher information balances the volume compression rate. And you can even have some more complicated thing that's a little bit more subtle. So that's what a Fisher information generally is. And it's less surprising to see it here than maybe me just throwing it out of the blue. There is a relative entropy formula for the Lyapunov exponents due to Baxendale. It's just complicated. I don't have time to discuss it. And you can take the time derivative of that formula and kind of derive this formula formally. But you can also just derive this formula by pairing the Kolmogorov equation with log and integrating by parts like a normal PDE person. So we found an easier proof later. It's kind of directly from the PDE. So that's the true formally, at least. And the great thing about this formula, so once you add the epsilons in, it comes out to this formula. The great thing about this formula is that it's stated at a non-negative quantity on this side of the equation, and it's directly on the stationary measure. So it's both simple and non-negative. So it's nice kind of additive quantity on the right-hand side, or sorry, left-hand side. It also has to do with regularity. So in particular, the Fisher information is a little bit stronger than saying you have W11 regularity, roughly speaking. So this essentially says that your W11 norm bounds from below this quantity of the Lyapunov exponents. And notice these epsilons will cancel. So you have something like n lambda 1 divided by epsilon plus 2 times the trace of A. And now this is the main technical step of our regularity method for estimating Lyapunov exponents, and it's a uniform Hörmander inequality. So it's yet another uniform Hörmander, but now in terms of the Fisher information. So if I have a solution to the Kolmogorov equation, if I know the Fisher information, and these vector fields span the tangent space of the projective bundle or the sphere bundle, it's the same, then I can control regularity in all directions uniformly just using the Fisher information, at least some fractional WS1 regularity. And so that immediately gives us a lower bound on the Lyapunov exponents in terms of this regularity. The point is that this C doesn't depend on epsilon. Just like, all right, so how do we prove this? It's actually still using Hörmander's this is a more complicated extension of Hörmander's proof. And the big difference is because we're only allowed to use the Fisher information, we have to use we're stuck in kind of W11, which means our dual space estimate isn't an H-1, it's W-1 infinity. So now we have a weaker estimate on the drift vector field, or yeah, just very different estimate, let's say, on the drift vector field. And so this is controlled by the Fisher information for our projective process F. And so the estimate that we're really trying to prove is this uniform Hörmander estimate. It's kind of a W1 or WS1 uniform Hörmander. And this different framework of W-1 infinity means that the regularization procedure it's already really complicated in Hörmander's paper, and we had to make it even more complicated, make it a little bit more subtle to handle this different regularity class. L2 is really the natural thing for doing this, but you can still do it in L1 and L infinity. And you can do it in a way which is uniform in epsilon, and that's the key thing. So this inequality will be uniform even if you have epsilon dependence in the vector fields. And so that gives us this lower bound. So for our systems, it tells you, well, we can formulate the following conditional theorem first. For all Euler-like systems, including Galerkin-Navier-Stokes, that if you can verify projective spanning, then not only do you have chaos for epsilon small enough, but you also have this probably very suboptimal, but still a quantitative lower bound on the Lyapunov exponent as epsilon goes down to 0. And verifying projective spanning is not trivial. So the only reason that I don't have a theorem for Galerkin-Navier-Stokes is this. Of course, now that you see this theorem. So we don't know how to verify projective spanning for Galerkin-Navier-Stokes, but we do know how to do it for Lorenz 96. So now let's see how to prove this conditional theorem. So what it comes down to is we have now this estimate for regularity of the stationary measures. And this is just true uniformly in epsilon, no matter what's happening. If this were to remain bounded, so if lambda1 divided by epsilon were bounded, then this would give us a uniform regularity estimate on the stationary measure of the projective process. So normally that's actually not going to be true. This is a definitely very much contradiction hypothesis. So if this uniform bound were true, then we would get compactness of f epsilon and be able to pass the limit and construct an L1 stationary, so an absolutely continuous stationary density for the deterministic projective process. Not just the deterministic X process, but the deterministic XV process. And it turns out that's very rigid because remember, growth of the gradients of the flow map will imply concentration. And so it should be pretty hard to get an L1 stationary density for a projective process in a deterministic Euler-like system. And you can actually prove, you can prove using the special structure, the bilinear structure and the energy structure of the system, that you can prove that there at least is a some growth. Of course, we don't know, I don't know how to prove positive Lyapunov exponents for deterministic Euler. That would be really, really hard. But we can prove some growth for deterministic Euler. And that's sufficient for this theorem. So that's one of the nice things about this theorem. So in particular, the important thing is it's really robust to your knowledge of phase space. That's why we can apply it to things like Lorenz 96 in 500 million dimensions, because we don't need to know this complicated dynamics that Lorenz 96 has. We just need to know something, essentially. Right, so this is the final theorem. So it suffices, okay, we had I think there's an off by 1 error, and we only prove it for dimension 7 and higher, but it very much includes 40 and up. That basically, if you force two consecutive unknowns with stochastic forcing, then Lorenz 96 is chaotic for epsilon sufficiently small. So the only thing you have to do at this point is to prove projective spanning. We also proved it for classical shell models. If you know them, they're called Goy and Sabra, for finite dimensional versions of Goy and Sabra. So we have chaos for those shell models as well. But again, not yet for Navier-Stokes. All right, I don't have time to explain how to prove projective spanning. It's neither impossible nor easy. One big step is to essentially say that, at least for something like Lorenz 96 or Goy and Sabra or Navier-Stokes, we can reduce the question to a matrix Lie algebra question. So you look at these kind of second derivative matrices of the nonlinearity. Now it doesn't, so notice that projective spanning no longer has anything to do with the forcing directions essentially. So if you're hypoelliptic in the x variable, then you just need to check some completely agnostic condition in the v variable. Just these matrices that have to do the nonlinearity, whether or not this matrix Lie algebra thingy spans all possible SLRN matrices. It's possible to check with a computer, which is actually something we do to prove for Goy and Sabra, but anyway, we don't have a really slick general method. We kind of, for Lorenz 96, we just played around with these matrices until we were able to prove it, essentially. And sort of, Goy and Sabra is a little bit more complicated, but still kind of ad hoc. So that's one of the tools that's missing. Okay, so just to summarize, there should be a lot of room to improve this chaos estimates. So we kind of hopefully, we're just kind of scratching the surface here, because you don't really want to depend on compactness rigidity arguments for all time, because you'll always get kind of a bad estimate. And kind of, yeah, you'll always get a kind of very naive estimate, whereas as you learn more about the system, you want to be able to get better and better estimates. And that's one of the things I hope is good about the problem, is that it's very robust to your information that you have. So hopefully as you get a little bit more information, you get a little bit better estimates. We'll see. But there's lots of places that one can improve, which I'm not going to list. Of course, infinite dimensions was our original goal. Everything that I talked about in this talk was very PDE, right? Everything was Kolmogorov equation this, Kolmogorov equation that. And extending these sorts of techniques to infinite dimensions is really challenging. And yeah, there's many reasons why we're kind of far away from using these techniques to prove things in infinite dimensions yet. But that was the original motivation, and I still think that we have some new and interesting directions to take the work in, even if we can't go there yet. Okay, so thanks everyone for your attention, and just please ask me some questions.